In the previous session, we looked at definite integral. Now let's look at indefinite integral. So given a function f of x, let us start with Riemann sum with variable upper limit. So this is the function, and we start with a Riemann sum with variable upper limit k equal to 1 to n of f of t sub k minus 1 times delta t. So to actually represent that, let's take a point A and let's take a point T. So in this interval, we want the area under the curve. So we take f of A and we take f of T and we build the rectangles. Let's join A and B T so that we have a bounded area. So this is the area under the curve using Riemann sum. Now here T is a dummy variable kind of thing, because x we are going to use it for the variable upper limit. That is, divide the interval a comma t into n sub intervals of width delta t, which is equal to t minus a by n. Now consider a very small increase in x, that is dx. Very small is called a infinitesimal. So let's do that. X is very close to t. Let's take f of x and let's join these two. Now instead of showing the Riemann sum, those rectangles, let me just make it a smooth one so that we can see it clearly. Now the interval becomes t comma t plus dx, the interval between these two, and it would be extremely small. Width is dx, which is infinitesimal. Height of the tiny rectangle is approximately equal to f of x. Then the extra area dA is approximately equal to the height times the width. So height is f of x approximately, and dx is the width, which we can write it as dA by dx is approximately equal to f of x. Take x closer and closer to t. So which means as dx tends to 0, dA by dx becomes equal to f of x. By definition of the derivative, we know dA by dx is equal to the limit as dx goes to 0 of a of x plus dx minus a of x by dx. So what do we have? We have dA by dx equal to f of x, and we have dA by dx equal to this. So we can say f of x equal to dA by dx equal to limit dx tends to 0 of a of x plus dx minus a of x by dx. So which means what? Any function, say capital F of x, whose derivative is f of x, is called an antiderivative or indefinite integral and is written as integral f of x dx equal to capital F of x plus c. So capital F represents the integral expression and c is the constant of integration. Why we require this? I'll come to it later. So here f of x is called the indefinite integral of f of x and c is called the constant of integration. What is interesting here? Interesting aspect is that the function describing the accumulated area under a curve f of x is equal to the integral from a to x of f of t dt has a rate of change equal to the original function, which means we can recover the original function by evaluating the rate of change of area under the curve. So in other words, if we have an integral, if we take the derivative of that, we get the original function. This is called the first fundamental theorem of calculus. And this is the link between differential calculus and the integral calculus. Otherwise, also you can think of it like this. As I come from minus infinity towards positive infinity, what happens? The accumulated area under the curve keeps increasing, and it keeps changing based on this curve, the original function. So here the accumulated area keeps decreasing, and then it starts increasing. Then it again starts decreasing. Then it again starts increasing, decreasing, increasing, decreasing. The main concept is that the integral calculus and the differential calculus are related. Where if you take the derivative of the integral, you get the original function. Now, this capital F of x, that is integral, is also a function. So which means we can plot it. So when we plot it, we get something like this. And importantly, whether this graph of the integral, whether it is here or whether it is anywhere else, it represents the integral exactly. So any one of these curves could be the one which we are interested in. Or in other words, the integral always gives us a family of curves. Since it gives us a family of curves, we add a constant of integration. If we are interested in the specific one with respect to a particular context, then we require some additional information based on which we can evaluate the value of C. So that is how C comes into picture. Of course, when we differentiate this to get back the original function, what will happen? C will disappear because it's a constant and we'll be left with f of x. That was indefinite integrals. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.